Hello, guys.
Hello.
Hi.
Hi. Are you okay?
Me?
Yes.
Yeah, we got power back, so it's all good.
Okay, good.
Yeah.
Yeah, we didn't do much things last time. We just went over, I think, one or two examples.
Okay.
I think you're good. Have you looked at those examples?
I just looked over the notes, but I really couldn't remember where we stopped last time because it was Friday. So after today, I'll look back and see what we did last time.
Mm-hmm. Will you please take the presents? It's 1 o'clock.
We're missing 2 people.
2 people?
3 people.
Who are they?
Let's see.
You can send the email to me if you want.
Okay. Jack Hill. Oh gosh. Catherine.
Okay. Misa, right?
Yeah. Hill, Nazar, and one more. Michael Jackson.
Why Michael Jackson is irregular nowadays? Catherine is here. I don't know why she is not here today.
I don't know. They might join in a little later.
No. Gerald, how are you? Gerald. Yes.
I'm doing good, sir. How about you?
Yeah, good.
Mhm.
Fraser.
Doing pretty well. How are you, sir?
I'm okay.
What happened to your neck, sir? If I may ask.
I don't know, but last week the pain started from the back of the neck, and then after I went to the doctor, and doctor said that I have to use this belt for a few days. And then after he sent me to the physical therapy, and he gave me some exercise for the neck. And he asked me to take Advil if it is required. So some pain because constantly I'm working on the laptop and computer. So probably that's why I have some pain over here on the right shoulder and the neck.
Right.
Yeah. But I will be good. I'm quite good today.
That's good.
It was not possible for me to touch my chin on the chest.
Really?
Yeah, but today I'm good. Quite good.
I don't think
First idea.
that's hard for everybody.
Okay, guys, let's start. So, Samantha, we went over this type of thing in practice test 5. First example, second example, third example, fourth example, and fifth example. And last time we did the 6th one. Am I right, guys? Last time we just went over a few definitions for the moment of inertia and radius of gyration for the lamina. And I told you that first of all, you need to find the mass and the center of the mass, and then moment of inertia and radius of gyration, right? Today we are going to start the triple integration. So please be careful, guys. We are almost at the end of our course. Question 7, 8, and 9. How many more classes are left out? Which one is the last day of the end of the semester? You have any idea? And
Friday.
our exam, Calc 3 exam is on which day?
Oh, I don't know.
You don't know?
Nope.
Jackson Marcia, you don't know?
No.
Nope, not at all.
Nobody knows this thing? Oh, that's not.
I'll look it up really quick. I think it's somewhere in my email.
Or you can just Google it. You can write VMI exam schedule, spring 2020 exam schedule, and you will get it. Hello, Les. How are you?
Good. How are you, sir?
Les, are you on moon?
Yeah, I don't know. What are you?
Hey, what are you doing out there, Lace?
I don't know.
You
I mean,
don't-
I think I might start flying around.
See?
That's my ship.
Will you please figure it out? Our
It's on Saturday
mm-hmm.
from 2. It's Saturday, the 9th of May from
9th
2
of May.
to
Okay.
5 p.m.
May 9th and 2 p.m. to 5 p.m., right?
Yes.
Is our final?
Yeah. Mm-hmm.
It's on a Saturday.
Which one is the last day of the teaching?
11th of Monday or 11th of May. So Monday.
No, he's asking what day are the final classes, not final exam.
Oh. I think it's the 5th of May.
4th. I think the 4th.
4th of May.
Oh, yeah, because we probably get a day in between
Yeah,
exams.
reading day.
So 4th May is the last day of teaching. Okay. And May 9th at 2 p.m. our exam is scheduled. Okay. Sounds good. May 9th is Saturday, so I will try my best to post your grades or submit your grades by Sunday. And
So the first of April is our last lecture then? Is that right?
Reading day. 1st
Oh, no,
of
the
May.
4th is. Right, my bad. Wait, no.
last lecture will be on 1st of May, right?
Looks like it, yes.
Guys, 1st of May is the last class. Okay, so today is 16th and then 17th, 18th, 19th, 28th, 21st, and 23rd. Okay, so 4 more classes to go. Am I right?
Oh, if we have 3 a week.
I counted
Oh,
6.
3 a week. Oh, okay. Yeah, Friday. So 6 more classes to go. Wow, we have enough time. Good.
Well, 8 if you include today and tomorrow.
Today and tomorrow, yeah. I don't count today and tomorrow. Okay, guys, let's start with this one. So use triple integration to find the volume of this one. Now look at over here. If you look at example number A, upper hemisphere. Each word has its own importance. Upper hemisphere of this z equal to x square plus y square plus z square square root x square minus y square minus x 1 minus x square minus y square is equal to. Right now, if you remember Article 11.8, if I'm not mistaken, Article 11.8, if you remember, I gave you 6 figures, 3-dimensional figures. That was paraboloid, hyperboloid, hyperboloid of 1 seat, hyperboloid of 2 seats, paraboloid, ellipsoid. Am I right? If you try, yes or no, guys?
Yes.
Yes.
Yeah, if you try to memorize those page, that page, you will find this type of things. Here you can see here, if you are squaring both the sides, that means you are going to get squaring both the sides, z square equal to 1 minus x square minus y square. Send this x square minus y square to other side, means you are going to get x square plus y square plus z square equal to 1. So naturally, all plus signs and all squares, x square plus z square, that means that is the ellipsoid, right? So upper hemisphere of the ellipsoid is same here. X square plus y square plus z equal to 16. If you divide by 4, you're going to get x square plus y square plus z square by 4 equal to 16, means 4, right? This is ellipsoid. This is the paraboloid because power of z is 1. Here is x square plus y square. So paraboloid bounded above by the bounded above Please keep in mind this thing. So lower bound we don't want. By this sphere x square plus y square plus z square equal to 6. Right? So these 3 examples are there. We are going to see one by one all these 3 examples. So let's start with this one. Let me start with, first of all, triple integration. What we mean by triple integration. I think last time I started triple integration, right? We solved just one example. I told you triple integration always gives you a volume. Double integration provides you a region. So triple integration gives you a volume. So once you solve for z, that means you are converting your volume to area. So triple integration always gives you a volume. Just keep in mind this thing. So here question number 4, and then okay, yeah, here. So I took this example last time, Samantha, that is for you. Look at over here, triple integration. And if you look at this circle, that is nothing but here, that is z runs from 0 to x plus y, 0 to x plus y. Sorry, previously I had just integration with respect to x and y, and I told you that inner integral might be a function of the out integration. That means here y equal to 0, the outside it is x equal to something. Most outer integral must be your constant. It should not be function of any other variables. So please keep in mind this thing, but inner integral may or may not be a function of the outer integral. So here y is a function from 0 to x, and z is a function from 0 to x plus y. So z might be a function of constants, or it may be a function of any one of these 2 variables or combination. So always keep in mind this thing. So triple integration again gives you a volume. So if you solve this triple integration, first of all, with respect to z, so e to the power x y plus 2z. This is e to the power x. You can do that thing that multiply e to the power x by this one and this one. But I would prefer to take this e to the power x out of here, because this part, I'm sorry, yeah, e to the power x over here. Because you can see over here, this is with respect to z. That means I want just z part over here. Thereafter, I want just y over here because it is with respect to y. And then after I want x. So I just would like to take this e to the power x out of these 2 integrals. Good. That means y plus 2z is left out. Now integration of y with respect to z is y is constant. So it is y times 1. Integration of 1 with respect to z is z. So it is yz. 2z is 2z square by 2. So it is z square. And range is 0 to x plus y. Range is 0 to x plus y. If you plug this value over here for z, so z is replaced by x plus y. So xy plus y square and x plus y square. There is x square plus 2xy plus y square. If you combine this thing, y square is 2y square, or like this, right? Or you can do this thing. You can go for the integration with respect to y. So integration x is constant, y square by 2, y cube by 3, x square y, 2x y square by 2, y cube by 3. You can do like this, y cube by 3. Okay, then plug the values, plug the range. So 0 to x. If you plug these values for y, you're going to get everything in terms of x now. So 0 to x. Everything is in terms of x now. So then after you can go for the integration, you can multiply this thing first. This with this one, this with this one, or you can do directly. So you are getting like this. Look at over here. This is the constant. After plugging the values, you are going to get this constant. So just pull this constant out of the integral sign. Here e to the power x and x cube. So e to the power x and x cube, that means that will provide you have to use the u into v, integration by parts, LIATE rule, where u is the algebraic function, e to the power x is an exponential function, stands at last. That means this is your v, this is your u. Just use u into v rule. That means this x cube will be converted to x square. Again use u into v rule. So your x square will be converted to power x, and like this. So 2-3 times you have to use u into v rule just to get rid of this part. And finally, you are going to get this expression. Just solve this one, and whatever you're going to get, that will be your answer. Just make sure you must get the answer in terms of some constant, because volume is just one real number, one constant. Now let me go through one of the examples. Example number B of question 7. 4x square plus 4y square plus z square equal to 16. I told you this is the ellipsoid. if you compare this one with the figure I gave you in 11.8 article, that formula sheet you can say, in which 6 figures were there. If you try to compare this equation with any one ellipsoid equation, you're going to get this one. Okay, so 4x square plus y square plus z square equal to 6. Now, first of all, ellipsoid would be like this. In 3 dimensions, the ellipsoid, that would be in this form. But I want to fix my range of integration. We are not provided any kind of range of integration over here. Please keep in mind this thing. We are just given 4x square plus 4y square plus z square equal to 16, right? Plus z square equal to 16. First of all, what I'm going to take, let me write z square equal to 16 minus 4x square minus y square. Just look at here, guys. I'm writing for you. Please look at over here. Probably this will give you a better idea. I have 4x square plus 4y square plus z square equal to 16. Means I can write z square equal to 16 minus 4x square minus 4y square. Z square equal to 16 minus 4x square minus 4y square. So z is equal to plus or minus 16 minus 4x square minus 4y square. 16 minus 4x square minus 4y square. Just look at over here. Shall we get this type of equation? Yes or no?
Yeah.
Yes.
Yes.
Right. Now, if you read, let me open my practice test. Just wait. Yes, it is. It says the ellipsoid, right? That means I have 2 values of z over here. So one z value is with respect to negative sign. Second z value that is with respect to positive sign. So my range of z, that will be over here. Just look at over here, the range of z. Only range of z. Don't look at any other thing. Just range of z. It's negative of 16 minus 4x square minus 4y square to positive of 16 minus 4x square plus 4y square. Agree? So z is fixed. Z is fixed. Now what I'm going to do? Now, because my z is fixed, that means z equal to 0 in the given equation. So now take z equal to 0. Now z equal to 0. That means I'm going to get 4x square plus 4y square equal to 16. That means my 4y square equal to 16 minus 4x square. That means y square equal to 4 minus x square. So y equal to plus or minus square root of 4 minus x square. Shall I get this equation now? Look at here, guys, please. If I take z equal to 0,
Yes.
z equal to 0. So that's how you can fix the range. Whenever the limit of integration is not provided at that time, we can fix the limit of integration this way. By taking z, once you fix the range of z, then take z equal to 0 so that you will be having the equation only in terms of x and y. Once your y range is fixed, now I'm going to take, now, suppose my y equal to 0 because z is fixed, y is fixed. So now let me take y equal to 0. Y equal to 0 as well as z equal to 0, right? Y equal to 0 in this equation. So I'm going to get 4x square equal to 16. So x square equal to 4. So x is equal to plus or minus 2. Agree? X is equal to plus or minus 2. Look at here. Yes or no?
Yes.
Yes.
X equal to plus or minus 2. Travis, are you here? Travis.
Yes.
Okay.
I'm paying attention.
Missar? Michael Jackson? What's wrong with these guys?
They're still not here.
Okay. So that's how I can fix my range. Look at over here, guys. This, and dy, dx, and dz, dz, dy, and dx. Once I have this one, now what will happen, guys? Look at over here. This dx, dy, dz, or dz, dy, dx, all are square functions, even function. That means I can use one of the formulas, Calc2 formula. Integration negative a to a. Every time I have negative and positive number, negative and positive, negative and positive. Whenever you have negative and positive number, that means it is 2 times f0 to a fx dx. It is like this, 2 sides. But whenever it is even number, that means you can overlap this one. So it is 2 times and 0 to the higher range. 2 times 0 to higher range. Fx dx, if f is even. If odd, 0. Here it is even, that means I'm going to get 2 from here, 2 from here, 2 from here, and all bottoms are 0. That means I'm going to get like this. Look at over here. 2 into 2 into 2. So 8, 0, 0, 0, and range, upper range, upper range, upper range. Just by using this formula. Now integration of 1 is z with respect to z is z. So it is 16 minus 4x square minus 4y square square root sine. Square root sine. Again, it's a good example. Look at over here. Question is, how can you integrate this function? Integration of 16 minus 4x square minus 4y square dy dx. How can you integrate this function? Integration that is with respect to only x square and y square, and you are going to integrate only with respect to y first. So your x is constant, means 16 minus 4x square is constant. Only 4y square is left out. Shall I write this integrand as, just look at over here. Just look at my cursor. Shall I write this integrand as square root of 16 minus x square minus y square like this? Look at here, please. My finger, please. 16 minus x square, because x is constant also. We are integrating with respect to y. Agree? All of you?
Yes. Yes.
Okay. So that's what I'm doing over here. Look at here. I just wrote it down in terms of 16 minus 4x square minus y square. Why? Because I have ready-made formula for integration a square minus x square equal to this one. I told you to write down this formula in your formula sheet. Right? So it is x by 2 a square. Your a is nothing but constant term. Your constant terms are here. That is actually, this is wrong. It should be 16 minus 4x square minus 4y square. Yeah, like this. 16 minus 4 minus x square minus y square. It should be something like this. I took this 4, 4 and 4 out. If you take 4, 4 and 4 out, so here it is square root, so because it's 2 out, so 16. Here it is 4 and 1 and 1. But x is constant, so let me join x with my constant. So this is my a square or a and minus y square. Y equal to x or x equal to y. 4 minus x square is your a square. 4 minus x square is a square. So what is your a? A is square root of 4 minus x square. Agree? A is square root of 4 minus x square. Are you getting me or not, guys?
Yes.
Repeat.
Yes.
Look at this arrow. Look at this arrow. My x in the formula, here it is. In my equation, it is y. X is y. And my a is nothing but, or a square is 4 minus x square. But I want a. No, I want a. So a will be, here a square is 4 minus x square. So a will be square root of 4 minus x square. Agree? Square root of 4 minus x square. So if you plug this here, y by 2 integration a square means 4 minus x square minus y square plus a square by 2. A square is 4 minus x square by 2. Sine inverse x and a is square root of 4 minus x square. And range is 0 to 4 minus x square. Range is this one. If you plus this range, sorry. If you plug this range for y, so 4 minus x square and minus square root of, see, y square is 4 minus x square. So this will get cancelled out. Everything is 0. Here 4 minus x square by 2, sine inverse 4 minus sine inverse 1 is simply pi by 2. So 4 minus x square by 2 multiplied by pi by 2, this portion, minus. Y equal to 0, everything is 0. 4 minus x square by 2, sine inverse 0 is, what is sine inverse 0? 0, right? So no need to write. Only 4 minus x square sine inverse x, that is pi by 2 will appear over here. So that is equal to this pi by 2, if I pull it out, so it is 8 times pi by 2, that is equal to 4 pi. So 4 pi. And here it is integration with respect to x, 4x minus x cubed by 3. 4x minus x cubed by 3. That means this term. Range is 0 to 2. Simplification gives us 64 pi. So that's how you can find the volume of the ellipsoid given in the form 4x square plus 4y square plus z square equal to 16. Just make sure here I gave you the full ellipsoid. I did not ask you just upper half or like this. I change my example to upper half. If I change my example to upper half means all bottom range are 0. So 0 to this, 0 to this, and 0 to this. Take this thing. Here I have not asked you upper half, the whole ellipsoid. That means I have to go for negative to positive like this. And then after I used this definition, this formula, calc2 formula, and I pull my constants out to do like this. And then after I just use this another formula and got the answer. Any doubt?
Sir, I've got a question. In that second to last line, you've got a 4/2 times the square root of 4 minus x squared.
4/2 where? Second last line, this one?
Yes, yeah, right there. Yeah,
Oh, it
you've got
is not 4, it is y/2. It's not 4. Look at over here. Here x is equal to y. So it is y/2. This is y.
Oh, that's a y. Okay.
That's y.
Thank you.
y/2. Okay. This is y/2. That's why I told you, just compare with compare with your formula. If you compare with the formula, you're going to get everything. See here, my y is x. So
Yep.
y. And constant a square is 4 minus x square. Okay. Any other doubt, guys? Every time we are going to use this thing, whatever I taught you, this thing to fix our range of integration. Every time. So please keep in mind this thing.
We use that formula every time.
Most of the times we are going to fix our range of integration using this technique. Would you like to see this example twice?
What do you mean by see it again twice?
I mean that just try to go through each and every line, because I want to give you one example to solve over here right now.
Well, maybe instead of that example again, could you do 7a?
7a, I would like to give it to you. Once you, and if you are not able to solve it, I will help you. But yes, I can do that thing. We will do it here. First of all, try to look at this example twice, each and every line. How I fix the range of z, then y, then x. C is equal to y equal to 0. Once you fix your range of integration, then the things are quite simple. Done?
No.
I'm just asking you to look at this example. I have not asked you to start the another example so far.
Oh.
Sir, I have a question.
Yeah.
And the formula that I wrote down in my formula sheet has the natural log instead of sine. Is mine incorrect? I need to
Which one?
the formula you have out there, the calc 2, or the a squared minus x squared, yeah, has an inverse sign at the end of it.
Mm-hmm.
What I wrote down in my formula sheet is a natural log. Is that something different?
Who
Or
is
is
there?
it-
Travis? Who is there?
This is Garner.
Say again?
What I have written down has a natural log, not.
No, but just make sure, is it a square minus x square or x square minus a square? You are misinterpreting.
In both cases, I have natural log.
No. Nope. If it
It's like a comes first, it has
formula is
x.
different. Is it a square minus x square or x square minus a square? Make
Oh,
sure.
it's x squared minus a squared.
Yeah, here it is a square minus x square.
Oh, okay.
Look at the difference, please. Right?
Yes, sir.
Travis, are you getting me? Sit.
Yes, sir.
What are you doing? Are you sleeping?
Me?
Are you sleeping?
No,
No.
no. I'm up.
Okay. Garner is here. So who is absent today? Misar and Michael Jackson, right? Two guys absent?
And Hill.
And Hill, yeah. Fraser? Fraser, how many bottles you have behind arms on the refrigerator?
Oh,
Number of bottles are there? Wow.
a lot.
That's good.
That's kind of the only way I can like handle continuing to do this math. Stay up late and drink yourself to sleep. It's very beneficial.
Okay, guys, shall we start the new one? Would you like to try number A? Upper hemisphere. Start.
I've been working on it, sir. I've been trying to do a little bit of it. I'm just
Sure.
confused
Where?
on the bounds of z. Would it just be 0 to the square root of 1 minus x squared minus y squared?
Again, it's not 0, it's negative. It's negative to positive. But
Oh, it would
I thought
just
we
be
were doing
negative. to
upper.
positive.
yeah, because I use this formula, whenever you have same numbers with negative positive sign, any of function is even at that time, you can multiply it by 2 and write 0 to a. So I use this formula here, and that's why it is 0.
But the question says the upper hemisphere.
Yeah.
Yeah, that is A. So in upper hemisphere, you are not going to do this thing. You are going to take 0 to upper part.
Okay. Yeah, that's what I was asking. It's 0 to the upper part. Yeah, that's what I thought.
So are you doing 7A?
Yes. Yes.
Okay, so all you guys can start 7A, please. Go ahead. All you guys can start 7A. Please go ahead, guys. So z equal to, yes,
What?
z equal to, your 7a says that z is equal to square root of 1 minus x square minus y square. So range of z is 0 to square root of 1 minus x square minus y square. Agree, guys?
Yes.
Because it is upper hemisphere, so bottom part is 0. Now if you z equal to 0, you are going to get x square plus y square equal to 1. Means it's a circle. So y square equal to 1 minus x square. So y equal to plus or minus 1 minus x square. So y equal to, now upper hemisphere means only range of z is 0, right? Range of y will be negative of 1 minus x square to positive of 1 minus x square. And if you take y equal to 0, x square equal to 1, x is equal to plus minus 1. So x is equal to negative 1 to 1. And my integrand is dz, dy, and dx. All of you are getting this one.
Yes.
Good.
Yep.
All of you, Samantha?
I'm just checking, and I think everything lines up. So yeah, I think I'm good.
Okay. So now solve this integral.
Oh boy.
Solve this integration. What are you getting? Square root of 1 minus x square minus y square. Agree? Are you getting like this, guys? Yes.
Yes.
Right. Because integration of 1 is z, and if you plug the range,
Yep.
you are getting this one. Am I right, Travis? Travis, you are confusing.
Yeah, so sorry, I was trying to flip through the screens, but let me see. Yeah, that makes sense.
Okay. Again, you have to use the same formula I gave it to you in the previous example. This is of the types 1a square minus x square form. Square root of a square minus x square form. Agree, guys?
Yes.
So x equal to negative 1 to 1, y equal to negative of square root of 1 minus x square to positive of 1 minus x square. And here it is. What was the formula? Formula was there on the previous page, and the formula was
X over 2.
sorry. Yeah, this one. So x by 2. So here it is y by 2 by 2 square root of 1 minus x square minus y square. Right? A square minus x square and plus a square by 2. So 1 minus x square by 2. And sine inverse of y over a is square root of 1 minus x square, and range is, yes please,
Negative.
square root of 1 minus x square. Agree?
Yes.
All of you agree with me. I just took the range. Look at here, guys. I just took the range 0, 0, and I took my 4 out. I took my 4 out. So that's why my range is 0 to square root of 1 minus x square. Agree?
Yes.
And I use the formula.
So all of them are 0 at the bottom
Yeah, because I use the formula.
because it's the upper. Is it because of it's the upper hemisphere?
No.
Well, no, all of them are 0 because there's like a rule above where you just add.
I use
add above.
look at the screen. I use this rule. Negative a to a fx ds is 2 times 0 to a. So it is 2 times this integral. Where is it? For this integral and 2 times for this integral. So 4 out and bottom 0, 0. Make sense?
Yeah, I guess.
And here I use the formula. Square root of a square minus x square formula. Agree?
Yeah, I think it'd be helpful if we got a picture of that, please, sir.
No problem. Right now.
The only question I have, sir, is when I'm looking back through the form, right before you switched it, like you changed the outer number 8 to 16. I'm not exactly sure
8 to 16?
in the step.
Previously, here.
Yeah, I'm just not sure exactly where you did that.
Look at here. Can you see this formula?
Yes.
Okay, what it says, my function integration range is negative to positive, same number.
Of course, I see how you got to 8.
Wait.
Yeah.
Whenever we have same number at that time, you can take this one as 0 and multiply this one by 2. That's what it says. Agree?
Okay. Yes.
Now I did that thing over here. I replaced this one by 0 and multiplied by 2 here. So this is out. Then after I did the same thing for this integral. Here it is 0, same range, and here 2. So 2 is out. Same thing here. Here it is 0, 2, and 2 out. Makes sense.
Yes.
So
it's just when you got 16 in the next step below it, just randomly.
16?
Right there.
No, this is 2, 2, 2 is 8.
Yeah, it's 8, and then right below it, just that
Just
one
wait.
line below.
Yeah. So here what will happen, see here it is 8, and this is 16 minus, means a minus x square form, right?
Mm-hmm.
2, 2, and 2. Why it is 8, right? Why it is 16? I don't know. Let me double check.
Yeah, that's what I was curious. I was
No.
wondering where you got that.
I'm good. Yes. Look, can you see here? This is,
Yeah.
what is my function? 16 minus 4x square minus 4y square.
Yeah.
If I can write this one. If I take 4 out.
Mm-hmm.
So 4 out, so 2 out. Here is x square, here is y square. So 4x square, y square, and this 2 out is outside. So 18 to the 16. Look at here.
Okay.
I took my 4 out. So 4, because of square root, I'm taking just 2 out. Agree?
Yes.
That's why it is 16 here. Makes sense?
Mm-hmm.
Okay. Anyway, guys, all of you agree with me up to here in this example. Les, he wanted me to solve this example. Les, are you good?
To be honest, I'm not good yet, but like once I look at your document for a while, I'll probably be good. Yeah, we can move on.
Okay, so
Wait, can I see that one more time just for a second?
No, he's gonna send it, James.
Perfect. Thank you.
No problem. May I take this page? Garnet?
Yes.
Okay. So then 4, x is equal to 0 to 1, y equal to 0 to 1 minus x square, and inside I have y is replaced by 1 minus x square, so it will be 0, 1 minus x square by 2, and sine inverse of 1, that is pi by 2, minus y is 0, 1 minus x square by 2, and sine inverse of 0 is 0. So that is equal to 4 out, x is equal to 0 to 1, and y equal to 0 to square root of 1 minus x square, and 1 minus x square by 2 multiplied by pi by 2. Let me take the picture and send to Samantha, and she will send it to you soon. Just wait for a minute, guys. Samantha, are you using WhatsApp? Samantha,
Sorry, you just text me.
are you using WhatsApp?
No.
No, okay.
Got to get on the new.
WhatsApp is faster than this one. Anyway, but I think you got it, right?
I will in a little bit. It's still sending. I got it.
Yep. Delivered, yes. Please send this, guys.
I will.
Yeah.
I'm doing it right now. It should have sent, so.
Okay.
Got it.
All of you, just try to look at that one. Try to look at the bottom and just one step is left out. Just try to finish the example by your own. All you guys agree with me or not? Example 7a.
Could you just reiterate why for the z variable you're going from the top to 0?
Not, yeah, actually.
Oh no, yeah, never mind. Because
Top
it's
to
like a
0.
hemisphere and it kind of
It's
like
upper,
curves.
it's upper half, that's why.
Yeah, but then the hemisphere kind of curves in both directions to the x and y axis.
X and Y axis, but hemisphere will go like this. So Z axis will not be there at that time. So that's why we start with Z equal to 0 and hemisphere is like this.
Yeah.
So that's why Z
And we need to
X and Y.
we need to plan for it kind of goes on both sides, but then it just doesn't cross to the negative Z. Okay.
Exactly. Yep. If you put this equation in MATLAB, you will have a better idea. Just put this equation in MATLAB and you will have the good picture. You know how to use MATLAB, right?
Of course, sir.
Okay, that's good.
We all know everything about MATLAB.
Everything. Wow.
No, I actually. Is there a 3D calculate, like a 3D grapher somewhere? Like
Yeah. Yeah.
I usually use Desmos for 2D stuff. I don't think it has 3D.
In MATLAB, we have 2D and sometimes 3D too. Yeah.
Is there something on the internet? Because like I don't have MATLAB on my laptop. No,
No, I think in MATLAB you will get 3D graph too.
Yeah, is there something besides MATLAB?
Yeah, Mathematica.
Oh, okay.
Yeah, Mathematica. Then after there is another software in which always you're going to get 3D graphs. That is, I forgot the name. But MATLAB and Mathematica, they are the powerful tools to get 3D graphs.
So like nothing that you could just like.
Samantha, did you get another picture from me?
Yeah, I sent it to everyone.
Okay. Guys, I just try to solve example number 7C also. Just look at 7C. I just set up the integral. Rest of the things you can do by your own. Example 7C, Samantha just forwarded to you. Done, guys?
I'm almost done.
Done with 7A. It's simple now, right? 4 and 4 will get cancelled out. Just pi is out. Integration of 1 minus x square is x minus x cubed by 3. Plug the values and you're done.
Wait, it wouldn't be x minus x3 over 3? It would just be 1 minus x to the third over 3?
No, not. It is 1 minus x by 2 right now, but integration will be x minus x cubed by 2.
Okay, yeah, that's what I got.
Yeah. I think I wrote down one more integral, so please remove it. Look at here, please, 7A. I wrote down, just by mistake, I wrote down 2 integrals. Already I took the integration and plugged the values, but even though I wrote the integrals, so just remove that y integrals.
Oh, okay.
Okay, and the last one is 7C is like this. Already you have it. So I first took like this, z square equal to 6 minus x square minus y square. So bottom range is like this. Then after I solve these 2 equations, I plug the value of x square plus y square equal to z. But I'm not going to ask you example number 7C in the exam, don't worry. That's why I put the cross sign. Are you guys done? Shall we go for the next one? Shall we go for the next one, guys?
Yes.
Okay. Look at here, guys. The next one is change of order of integration. Change of order of integration can be done by several ways. Several ways. Sometimes one integration can be written as 5 another ways. So total, the same integral can be written in the form of 6 different ways. 6 ways, yeah. 3 integrals and 6 ways. Just look at the first integral, guys. Just first example. Integration 0 to pi by 2. Now, integration x to root pi by 2 and z equal to 1 to 3. Sin y square dz dy dx. Because sin y square simply depends on y, let me just pull it out. That's fine. But that's not ultimate goal. Ultimate goal is to change the order of, and that means here it is given x, y, and z. You can write instead of x, z, and then y. Like this. Or y, then x, and then, z, then x, then y. Or x here, y here, z here. Or x here, z here, y here. Or y here, x, z here, and x here. Are you getting me? Or
Yes.
y here, z here, x here, z here, and y here. So in cyclic form, see here, x, y, z. Then after I can write x here, y here, z here. Then after I can write x here, y here, z here. Are you getting me? Then after I can change this one, z here and y here. So same integral can be written in 6 different forms. Let me just write it down over here. But before that, you have to have some picture to write your integral. X equal to 0 means y-axis, you know it. X equal to root pi by 2 means one vertical line along y-axis, agree? So x equal to, it's something like this. X is equal to 0, that is y-axis, x equal to 0. x equal to root pi by 2, vertical line like this. Vertical line like this. X equal to root pi by 2. Same way, y equal to x, line passes through origin. Y equal to x. And y equal to root pi by 2. Y equal to root pi by 2. Something like this. Look at here, guys. Look at here. Are you getting me, guys?
Yes.
Right? That means I am given this region. We are given this region.
Yes.
I just took x and y. Now, if you look at over here, look at my cursor. My integration runs from y to root pi by 2. Means y first and then x. Y first means vertical strip is given to us and then horizontal. Agree? I want to change the order of integration. That means right now it is given to me like this. Like this. Agree? Instead of that, I want to change the integration. So let me take horizontal strip like this. So this is x is equal to 0 and this line is x equal to y. Am I right? Am I right, guys?
Yes.
Yes.
Right. So what will happen? That means my integration will look something like this. X is equal to 0 to x is equal to y. And y equal to 0 to root pi by 2. Look at here. Y equal to 0 to root pi by 2. And my z will remain as it is. So z equal to 1 to what is given? 1 to 3 sine of y square dz dy dx. So my integral will look like this one. Agree?
Yes.
And I change the order of integration. See here, I started with x first and then y. I change my order. Look at here. I change my order. And then after you can just calculate. This is just simply calculation. The total area after this one, you're going to get what I did. Okay. Yes. So if you change this one, sine y square outside integration of 1 times z dz is z range is 1 to 3. So it is 3 minus 1 equal to 2. Let me pull this 2 out. So integration x equal to 0 to root pi by 2, y equal to x to this one, and sine y square. Right, guys? Sine of y square. Now, how can you solve the sine of y square? Integration sine of y square. You don't know. You don't know how to solve integration sine of y square. Am I right? Integration of sine x, you know. Sine y, you know. But sine of y square, you don't know. So that's why we require to change the order of integration. If we change the order of integration like this, look at here. dy dx is converted to dx dy as I told you. Vertical strip is converted to horizontal strip. And my x range is now x equal to 0 to y as I told you. And y is equal to 0 to root pi by 2. If you do like this, you are going to get the integration very easy way, because sine y square is constant now. Just pull it out, sine y square. And you are getting one more y over here. So y square equal to u will give you, because of this y and y square, you can use y square equal to u substitution. And you are going to get sine u du. And integration is quite simple. So that is the advantage of changing the order of integration. Sometimes your integrand will be in such a way that you cannot solve it easily. Just like sine y square, you cannot solve it easily. That's in that case, we require to change the order of integration to get the volume in a very straightforward way. So that's what we did here. Agree? So I just changed the one example I did here, question number 8b. Oh, I have solved 8a also. 8a is solved over here. I want you guys to go through this one. Not right now. That's just the homework. Agree? And tomorrow, again, I will be starting with example 8a. Sounds good?
Yes, sir.
Yes or no, guys?
Yes, sir.
Yes, sir.
Yes.
Yeah, so always you can change the order of integration like this. In next example, example number 9, we are going to change the order 3-4 different ways. In this example, example 8, A and B, just we are required to change the order of integration. That's why we just change the order, one order, and we are done. But in next example, I will let you know how to change the order of integration by multiple ways. How to change the order of integration by multiple ways. Here z runs from this one. So I just started with my upper limit, z equal to this one, 4z equal to this one. So my equation is this one, 3x plus 6y plus 4z equal to 12. And then after I make an equation of y here. So equation of y here. So that's why y will look like this one, y equal to 0 to this one. Look at here. Y equal to this one. See? So I change my z and y. My z will go here and y will go here. Y will be here and z will be here. That's how I change my order of integration. Okay, let me spend a couple more minutes. Z equal to this one. I want to change my y over here and z over here. Another way. Let me start with the higher range. I first make my complete equation 3x plus 6y plus 4z equal to 12. Here it was made an equation of z. I want to make an equation of y. So 3x plus 6y plus 4z equal to 12. So 6y equal to 12 minus 4z minus 3x. Divided by 6, so 6 here. It is 0 is less than or equal to y is less than or equal to this one. Y runs from 0 to this range. 0 to this range. So that is my first integral. Y runs from 0 to this range. 0 to this range. That is my first integral. Now if I take y equal to 0. Y equal to 0. That means 3x plus 4z equal to 12. So 3x equal to 12 minus 4z. So x equal to 12 minus 4z divided by 3. So x runs from 0 to this one. So that is my x. Now if I take x equal to 0. So x equal to 0 means 12 equal to 4z. So z equal to 3. So z runs from 0 to 3. 0 to 3. That is my outer integral. If you evaluate this integral, you are going to get the same one. You are going to get the same evaluation. So you first evaluate, this is homework. I just leave it to you. Evaluate this one. Use this one. All this range of integration. Plug it over here and evaluate this one. Make sure you must get the same answer. So tomorrow, before I proceed further, I will ask you to show me your evaluation here and here. And I just want you to go through these stuffs. Sounds good? Yes or no, guys?
Yes.
Yes, sir.
Yes, sounds
Okay,
good.
so let me stop over here. And tomorrow is 2:10. Tomorrow is, we are going to solve example number 9. Tuesday, review session. Thursday, exam. Okay?
Okay.
Wait, when's the exam?
Next Thursday.
Okay.
Tuesday, Thursday exam. Tomorrow, completion of this chapter 9, example 9. Agree?
Yes, sir.
Yes.
Yes.
Okay, guys. Shall we stop here?
Yes.
Sounds good.
Okay, guys. Thank you so much for your cooperation. And yep.
Bye, sir.
Bye. Thank you, guys. Bye. Take care. Hello, Blaine.
Hello, sir. How are you today?
I'm good. I'll be back. Just give me 5 minutes.
Okay.
Yep. Zach, how are you?
Good, sir. How are you doing?
I'm good.
Good.
Yeah, you asked me something, but I didn't go over this one, so probably I will do this thing today night, and I'll let you know. Okay.
Okay, sounds good. Thank you.
Question 2, right? I have not seen that part.
It was question 10 from assignment 2.
Assignment 2, question 10. Okay.
Yeah, so they're yeah.
No problem. I will look at this one and let you know.
All right, thank you.
Yeah. So we are almost at end. So question 10, assignment 2, right? You said?
Oh, yes, sir. Yes, sir.
It is same as, see here, P, Q, and X are there, right?
Yes, sir.
Yeah, so which method is appropriate for P, Q, and X?
I have f of p q equals 0.
F of P, Q equal to 0? No.
That form? No, so that form's not
Only
there.
P and Q are there. F of P, Q equal to 0. So that won't work here.
Okay. And that might be my problem, using the wrong.
Yeah. Most likely here, in my opinion, this method will work. Not ZPQ will work, but you know, method B, PX plus QI plus FPQ, because FPQ is there and X is there. So that method will work over here.
Can you say that one more time?
Yeah, second type. PX plus QI plus F of PQ. EX plus QI plus F of PQ. But if you start with first method, let me see what's wrong with the first method. I think it will also work over here. Z equal to AX plus BY plus C. That's the solution, and A and B are replaced by P and Q. So AX plus QY. Your additional X is there. So what I would do, root P equal to 2X. So dx by X, dy by Y, dz by Z. So P square plus Q square equal to this. And yeah, I think second method will work. Second or first, just try with second one. And if you're not getting, okay?
All right, sounds good. Thank you, sir.
Yeah.
How are you doing, sir?
Hey, Daniel, I'm good. How are you?
I'm pretty good. It's a nice
Good.
day.
It's really very sunny over here, but very windy and cold also outside. You cannot go outside without jacket or like this.
Yeah.
Last week was good here, but this week is not good. Where is other guys? Fleming?
Sir, I'm here. Can you hear me?
Yes, I can hear you. And
Yeah.
then Mike.
Zoom's not working on my
here.
laptop, sir.
Mike is here, Valenzuela, yeah. And
How are you, sir?
yeah, Daniel is here and Jennifer is here. Good. Okay, guys, let's start. Did you see the Canvas? Did you check your Canvas? I told you last time that I'm going to post your assignment on Canvas. Have you checked it? In Canvas, I posted 2 items. One is application chapter, last chapter, that is in your syllabus. And in assignment, I have posted all your 1 to 10 assignments.
In assignments, it has
The due date,
PDE plus
yeah.
applications.
Yes. PDEs plus application. No, that is not the assignment. That is the chapter, last chapter, whatever we are working with right now. But if you go to assignment.
Because I'm looking in assignments, sir, and that's the only assignment there, PDE plus application.
Okay. That's the only assignment you have?
Correct.
So are you saying this thing in syllabus or assignment?
I'm looking at the assignment. I'm in the assignments tab. It says upcoming assignments, and beneath that, it says PDE plus applications. When I click on it, it says it's due April 30th, and
correct.
It's available from April 16th through April 30th.
Correct. So means you can find all the assignments over there, right? 1 to 10. Will you please double check? Do you find 1 to 10 assignments?
Yeah. There's 1.
Yeah. Then
yes,
2,
1 through 10.
1 to 10 assignments are there. Due date is 30th midnight. Right. So now you will be able to upload your assignments over here. Make sense?
No, actually. Because when I'm looking at these assignments, it includes some of the application stuff. And since you said that just the pure PDE stuff is due Saturday, correct?
Yes, due Saturday, that is correct. But I want to continue with these applications also. So you all guys have to submit your PDE stuff by Saturday. And then after, I just put one date over there. If you want, I can just write the date till Saturday. And then after, I can change the date, another date till April 30th. Or I can just give you one date and you can submit, all you guys can submit your first assignment before Saturday night and last assignment before 30th. What do you want? You want me to change the date or just you want me to keep the same date?
Sorry, I'm confused. My problem was I just thought that there was supposed to be 2 separate assignments. So it was, you would need to create another assignment to be able to turn in the applications portion.
No, look at over here. This is application. Let me just go to the bottom of this one. See here, look at here. This is assignment number 10, right?
Yes.
So I put all the assignments over here. I did not mention that you have to go only up to this one before Saturday. This is assignment number 8, which you don't have to do before Saturday. That is before 30th of April. Same here. Assignment 7, that will be before 30th of April. And this is application. So last assignment, that was this one, assignment number 6. So you need to wait 1 to 6 before Saturday night, and 7, 8, 9, and 10, that is before 30th of April. Sounds good?
Yes, sir. I mean, that's what I was saying, but that wasn't my question at all. I was just wondering if when you were going to create another assignment that you like an actual submission thing on Canvas so that we could turn in the other portion on April 30th, because
okay, I will do that thing, but actually, you know, I don't have scanner at my home, so I'm scanning all these things from my cell phone, but I will try it again and I will submit. I will make this in 2 parts. One is 1 to 6 and second one is 7 to 10. That's what you want.
I mean, it's fine if you have them in the same document. I don't think anyone cares about that. We all know what's due when.
Right.
I'm just talking about the logistics for submitting the separate assignments on 2 different dates. You never mind.
Okay. Okay, I got it. I will mention that thing. So you want me to mention that assignment 1 to 6 that is due before Saturday night, and 7, 8, 9, and 10 that's due before 30th of April. That's what you mean, right?
No, not really, sir. I'm just saying you can't submit 2 assignments in the same
Oh,
assignment on
okay.
Canvas.
Are you
So
sure? Are you sure?
I'm very sure it'll erase the other one because it'll cause it to be a resubmit.
Okay, got it. Because my other section, Calc 3 guys, they submitted homework as one assignment and their exam as second assignment, both separate assignments just in one section. But I'll do it. I'll make it into parts. Okay.
I mean, maybe it'll work, but I feel like that's tempting fate.
I think,
Okay, that's fine.
I think
But-
that when you submit an assignment, you can choose to add another file.
Yes. Yes.
And so that's probably how the other section of your class did that. So.
Yeah, I told them that first you submit your homework exam and then your homework. So they did this thing, and everyone they submitted separate files, 2 separate files, just in one section. Means I just posted exam and they submitted 2 separate files. One is for exam, one is for assignment. So just try it. If it is not possible, Jennifer, please let me know. I will make it into 2 parts.
Okay.
Right?
Sir, can I not still just share you a Google link to a folder I created?
I can't hear you.
Files.
I'm getting some echo voice.
Sir, just still.
Hello.
Sir, can Johnny and I just do a Google Drive folder?
Google Drive folder, okay.
The scans of all our stuff.
Okay.
Remember the other said I could just email you that?
Hello.
Do it.
I'm not getting you. Your voice is completely echo. I can't hear you clearly.
I can
yes.
say what he said. He said, is it okay if Garner and I turn in a Google Drive folder and send it to you via email instead of submitting something on Canvas? Will you?
Why you want to use Google? But I think you can submit on Canvas. But if you want to submit with Google Drive, I don't mind. That's fine.
Yeah, I think we got it, Garner. We can use a Google.
Yeah, you can use Google Drive. You can make a link and you can send that link to my email. And I think that sounds good to me.
Cool. Okay, thanks.
No problem. Yeah. Okay, guys, shall we start? Guys, shall we start? I'm asking you guys, shall we start?
Yes.
Might as well rip the Band-Aid off, sir.
Yeah, sir, let's go ahead and start class,
So, non-linear PDE in a second order Monge's equation, that's what we decided not to do this thing right now. We will decide this thing later on. And then after we started the applications of PDE, the first application of PDE, that is the wave equation in 1 dimension. And then after we are going to see the heat equation in 1 dimension and then heat equation in 2 dimensions. That is called the Laplace equation in 2 and 3 dimensions. Okay. Jennifer, she helped us out last time. She did all these things and finally we figured it out. I think this one up to here, right? So what are the benefits? I mean, say where we are using this partial differential equations, what are the benefits, boundary value problem. So initially we have to work with our problem with the boundary values. It is not like our differential equation. In differential equation, usually we are using the boundary value or the initial values at the bottom of the equation, bottom of the solution to just find the value of the constants, but that's not the case over here for PDE. Whenever we have PDE at that time, first we use our initial value or boundary value and initial value, I would say, and then after we'll proceed for the complete solution. So that's what we figured it out last time. And now method of separation of variable. So first method, that is separation of variable. Did we do this thing last time? I think so, right? Guys, John, Daniel, what are you doing? Daniel, what are you doing?
I was tying my shoe.
Yes, Jennifer, did we do this thing last time?
We did.
Okay.
We did the second example as well.
Yep. So this was the first example, and I told you that because it is u is a function of x and t. Let me just revise this thing very quickly. So it is x and t. So you can write u equal to x and t. X is a function of only small x, t is a function of only small t. So this is the derivative. Just plug these values over here so that you're going to get this separable variable like this. Once you separate the variable, because x and t, they are the independent variables of each other. So that's why we can write this is exactly equal to some constant k. Once you write in terms of constant k, then after you can solve, because now this is just one variable and constant, another variable and constant. That means it's a difficult differential equation. You can solve this differential equation in this form. So x equal to c1 e to the power kx and t equal to this one. So once you have x and t, because you assume that u equal to xt was the solution, just plug it back. Means you are going to take the product of these two equations, these two solutions, x and t. So you are going to get u of xt equal to this one, c1 e to the power kx, c2 times e to the power this one. And then after I have used this initial condition over here to fix my values of the constants, and finally I got this one. And then after, as you guys know, that we went over the second example too, that here you can see z is a function of x and y. So let me write z is equal to capital X and y, where capital X is a function of x only, small y is a function of just small y only. And then we require second derivative over here. So plug the values over here, the second derivative, first and first derivative with respect to x and y respectively. Just plug it back, and finally you are going to get separable variable like this. Again, x and y, they are independent, so that is equal to some constant k. That means it is differential equation. If you solve this differential equation, you are going to get, this is the quadratic equation, and quadratic equation capital X is given in this form because you are going to get m square minus 2m minus k equal to 0. So m equal to this one. And here y is equal to this one. So x and y again will give you this solution. And then after, we don't have any, we don't have any boundary conditions or initial conditions provided over here. That means whatever we are getting over here, that is the solution. I just wrote it down, this C1 and C3, that is equal to some constant A. Otherwise, you can leave this one as it is. Okay, and then after I gave you these 3-4 examples in homework. Okay, so now we are going to start the vibration of straight string one-dimensional wave equation. Vibration of straight string one-dimensional wave equation. Guys, please pay attention over here. Please pay attention. Oh, why is this not working? Okay. Okay, guys. Valenzuela, will you please read this one? Just like Jennifer. She read this one last time. Will you please go through this one slowly? Just keep in mind this thing, guys. Whenever you have wave equation, at that time you have square on both the sides. So del square y by del t square equal to c square del square y by del x square. You must be curious that how we are getting this equation, or why this equation is called the wave equation. Whatever we are doing right now, you guys are the least concerned as far as concern of your homework problem or exams or like this. This is just for your knowledge. How this equation is generated, that's what I have proved over here. And that's what we will go over this part. But again, you are the least concerned about this. Just read this one. And if you are curious, otherwise it's good. Look at over here. Consider the uniform elastic string. So you have one string and one end of the string is fixed, second end is fixed. And here it says that vibration, if you pull the string in the middle of the middle part and leave it, the string is vibrating. And in that case, we are going to get this equation. So vibrating string equation that is in this form, del square y by del t square equal to c square del square y over del x square. Right, guys?
Mm-hmm.
Yes, Valenzuela. Will you please start? Mike. Yes. Go ahead.
Where do you want me to start, sir?
I want you to start with this one. Consider a uniform elastic string.
Consider a uniform elastic string of length L stretched tightly between 2 points, O and A. And
Look at over here. O and A is over here. This is O and this one is A. Uniform elastic string of length L. So this length of the string, that is L. This length is L. Okay, go ahead. And
taking end O.
Displayed slightly.
Oh, and displaced slightly from its equilibrium
OA.
position OA.
Right? Displaced slightly from the equilibrium position OA. Right.
Taking end O from its origin, OA as the x-axis, AR.
And perpendicular line through O, that is your y-axis. Right? We can find the displacement y as a function of the distance and time t. Right? Displacement in y, this much it will go, this much up it will go. So displacement of y, there is a function of the displacement and your time t. So that's why we can write this one as a function of u as a function of x and t. Okay, go ahead. We shall obtain.
We can find the displacement y as a function of the distance x and time t. We shall obtain the equation of motion for the string under the following assumptions.
Yes, we have to assume some of the things. 4 assumptions. The first assumption is, yes.
The motion takes place entirely in the xy plane, and each particle of the string moves perpendicular to the equilibrium position OA of the string.
Right, look at here. The motion takes place entirely in the xy plane. Right, just in xy plane, we are not counting right now any z part because it is just one dimension. So motion takes place entirely in xy plane, and each particle of the string moves perpendicular to the equilibrium position. This is the equilibrium position, it moves just perpendicular like this. It moves like this, perpendicular position OA of the string. Second.
The string is perfectly flexible and does not offer resistance to bending.
Right, so resistance bending, spring doesn't offer any resistance bending. We are assuming this thing too, and it's perfectly flexible. If string is not flexible, there is no point to find, do any kind of work over here. Third assumption.
The tension in the string is so large that the forces due to the weight of the string can be neglected.
Right, the tension in the tension in the string is so large, tension is large enough that the force due to weight of the string can be neglected. So force due to weight of the string, that is just neglected. And the last one is?
The displacement y and the slope del y on del x are small, so that their higher powers can be neglected.
Displacement y and del y by del x, they are just small, so higher powers means del square y by del x square and so on, all higher powers are neglected. So we are just working with y and del y by del x and like this. Okay, let m be the mass per unit length of the string. Consider the motion of an element pq of the length delta s. Look at over here, consider the motion of an element pq. You can say like this, this is x, up to here it is x, and this point is p, this point is q. This is t1 and this makes an angle alpha, and same way this makes an angle beta. This displacement in x is given by x to x plus delta x, so this one is delta x, actually very small. Okay, so let m be the mass per unit length of the string. Consider the motion of an element pq of length delta s. Since the string does not offer resistance to bending, the tension T1 and T2 at P and Q are tangential to the curve. This tension T1, this is the tangential, and tension T2, I did not write, this is T2. I think here it is, yeah. Tension T1 and tension T2, they are the tangent. So tangent at P and Q. This tangential is nothing but, or tension is nothing but the tangential line, that is T1 and T2. T1 and T2 at P and Q are tangential to the curve. Since there is no motion in the horizontal direction, just direct motion is in the vertical direction, no motion in the horizontal direction. That's why we can write T1 cosine alpha equal to T2 cosine beta equal to T, some constant. And the mass of element PQ is m times delta s. Usually we denote the mass like this. And by Newton's second law of motion, right, the equation of the motion is given in this form. So mass into del square y by del t square is equal to T2 sine beta minus T1 sine alpha, this difference. And then after, if you take just if you use this equation, first one, if you divide by this one, you're going to get m ds del square y by del t square divided by t, and that is equal to t2 cosine beta minus t1 cosine alpha. Just you divide respective terms. Send this constant to other side, you're going to get this sine over cosine, that is equal to tangent, so tangent. But tangent is nothing but a tangential line. Tangents at beta, that means it is x plus delta x, and here it is tangent at alpha, it is x. If you look at over here, tangent at beta, this is a beta. So this x plus delta x, this one is alpha, that is with respect to your x, because your motion is just the vertical, not the horizontal motion. And that's why we can write dy by del y by del x and del y by del x, x plus delta x to x. Good. Delta s is your delta x to our first approximation, and the tangent alpha and beta are the slopes of the curve of the string x and x plus delta x, as I told you. So del square y by del t square t over m, and all these things, this delta x's I would like to consider inside. If you take this one inside, then after what will happen? This is delta x. It means you can write f of x plus delta x minus fx over delta x. Just try to compare this one with your limit definition of derivative. X plus f of x plus delta x minus fx over delta x. So what is this? This is nothing but del square y over del t square. This is the constant. I would just like to denote by t by m, that is c square, and del square y by del x square. This is just a derivative in limiting position. So in limiting position is a derivative, and that's why the general equation for general wave equation that is given in this form, del square y by del t square equal to c square del square y over del x square. I'm sorry, guys. And we are given some boundary conditions like this. This is PDE given the transverse vibrations of the string called the one-dimensional wave equation. This is the one-dimensional wave equation. And it has to satisfy some of the conditions when y equal to 0, when x equal to 0. Y equal to 0 when x equal to 0. Look at here. Y equal to 0 when x equal to 0. And this length is L, so y equal to 0 when x equal to L. So y is equal to 0 when x is equal to L. Y equal to 0, x equal to L. This should be satisfied for every value of t. If the string is made to vibrate by pulling into a curve y equal to fx and then release it, the initial conditions are y equal to fx when t equal to 0 and del y by del t equal to 0 when t equal to 0. These are the initial conditions. That's fine. Now, how can we get the solution of this wave equation in one dimension? Del square y over del t square equal to c square del square y by del x square. Again, exactly the same thing. I told you that if you understand the first example, other examples, they are just similar. I told you last time, and still I am on my words. Look at over here, del square y by del t square. So it's a function of x and t, function of x and t. Y is a function, y is a dependent variable, x and t, they are the independent variables. So y is a function of x and t, x is a function of x, t is a function of t, both are independent of each other. We want second derivative over here, so del square y by del t, del x square means x double dash t, and del t square is x t double dash. If you plug these values over there in the given equation, you're going to get this one. As I told you, that is equal to some constant k because they are independent. So this is my ODE, this is my ODE. Again, I just repeat the same method, d square x over del x, dx square equal to xk. So auxiliary equation is d square minus x square equal to 0. So d square minus k equal to 0, d equal to plus or minus root k. So root are real and distinct. Means c1 e to the power root kx, c2 e to the power negative root kx. Here t square equal to t c square k. So auxiliary equation is d square minus c square k equal to 0. So d equal to plus or minus c root k. C3 equal to, already I use C1, C2 over here. So let me use the constants over here, C3 and C4. So C3 e to the power c root kt and e to the power negative c root kt. Instead of working with this root, because everything is positive, so that's why, just for the sake of convenience, I would like to take k is positive and that is equal to p square because there is no negative k. And that's why I just would like to consider this one as k equal to p square, so root k is p because it is positive. So I can revise my solution, or I can rewrite my solution in this form, x equal to c1 e to the power px and negative px. C3 e to the power cpt, c4 e to the power negative cpt, like this. When k is negative and negative p square at that time, in that case, you are going to get the solution in terms of sine and cosine. If that is, you can see over here, if my p is negative or k is negative, that means d square plus k equal to 0. So d square is equal to plus or minus root ki. That means you're going to get cosine p plus sine p. Cosine px plus sine px, or cosine root kx plus sine root kx. And if k equal to 0, if this k equal to 0, d square equal to 0, roots are 0 and 0, real and repeated. So c1x plus c2, c3t plus c4. So these three different roots are there. Now, according to the given conditions in the example, we are going to use these roots. Sometimes the first root will be possible for the given solution, given example. Third one will be possible, or second will be possible. Most likely, because your motion is just a vertical motion, that means we can go into curvature like sine and cosine. So most likely 99% we are using just the second case. Means when k is negative and it is negative p square, cosine and sine form. So various possible solutions of wave equations, these three equations, I just repeated this one, these three equations, y equal to, and y equal to. Y is a function of x and t, and x and t. But as I told you, mostly we will be using this one. I just wrote it down that out of these three, we have to choose that solution which is consistent with the physical nature of the problem. Since we are dealing with the problem on vibrations, y must be a periodic function of x and t. See, y must be a periodic function of x and t, and periodic function is only given with respect to sine and cosine, because sine and cosine both are periodic function with period t, period 2 pi, you can say. And therefore, the solution must involve the trigonometric terms, and that's why, accordingly, I would say that let me consider this as the solution. Means second one is the solution, c1 cosine pt, c2 sine px, or this one. This is the solution. Boundary conditions are given to us, as I told you, y equal to 0 when x equal to 0, and y equal to 0 when x equal to L. That's the initial and boundary conditions are given to us. Okay, if you plug these values, this boundary condition in this solution y of xt, that means we will be getting this equation. And once you get this equation, this boundary condition, you're going to get c1 equal to 0. And second part will give us c2 sine pl, that is equal to 0. Because sine pl equal to 0 means pl equal to n pi. Because sine pl equal to sine function is 0 only for pi, 2 pi, 3 pi, 4 pi, 5 pi, in general n pi. So pl equal to n pi, p equal to n pi by l. So I got my value of p, I got my value of c1. If you plug it back, you're going to get y equal to c2 sine n pi x by l and c3 cosine n, because c1 is 0. So c1 is 0. So only this part is involved now, c2 sine n pi x by l, c3 cosine, c n pi by l and t, n pi by l, c n pi by l and t. So that is the solution. That is the solution. These c2 and c3 are constant. So let me just put one constant an, and then cosine n pi ct by l plus bn sine n pi ct by l. And this sign, I just would like to write it down on the right side. And I just wrote this constant c2, c3 as an and c2, c4 as bn. That's it. That means finally I'm getting like this, adding up the solution, different values of n. For different values of n, we are going to get the summation, just 1 point, but we have lots of points over here in between 0 to L, length of the string. So that means we are getting summation of an cosine n pi ct by L plus bn sine n pi ct by L, and this one. So this is a Fourier series. You can see over here. This is the Fourier series. And that's what I told you, that whenever you are working with the wave equation, heat equation like this, every time you will be using the Fourier series to get the answer. Sometimes you may have some half-range Fourier series. Sometimes you may have the full Fourier series. Most likely these things are positive, because 0 to L like this, it's not 2L, it is 0 to L. So 0 to L, that means in this particular problem, we are going to use the half-range Fourier series. So look at over here, this is the half-range Fourier series. And that's the reason why we started our syllabus with the Fourier series. Then after we went through the PDE, and now in application, that means the combination of the PDE and the Fourier series. That's what I told you, or I have been telling you since the beginning of the semester. So this is the solution, an cosine n pi x ct by L, n pi ct by L, and sine of n pi x by L. This is the solution. If you apply the initial condition, when y equal to fx and del y by del t equal to 0, so take the derivative with respect to t when t equal to 0. That means you have two terms, y equal to fx when t equal to 0, del y by del t equal to 0 when t equal to 0. If you apply this one, you are going to get this one. This y equal to fx, y equal to fx. And that is equal to an sine n pi x by L. N sine n pi x, because t equal to 0, t equal to 0, that means this sine 0, this t equal to 0, sine 0 will be 0. So this term will disappear. So an cosine n pi x, sorry, cosine 0 is 1. So an and sine n pi x by L. An and sine n pi x by L. Okay, and if you go for the derivative, I did not take the derivative over here. It is just straightforward way. If you take the derivative, so del y by del t equal to 0 when t equal to 0. So in that case, you're going to get derivative of this term is sine n pi x by L divided by n pi by L. So you can take that one over here and bn, this bn. So finally, you are getting your equation in this form, equation 9 and 10. And this 9, what is this? This 9 represents the Fourier series of the function fx. And this an is represented by 2 by L because your length is 0 to L. So 0 to L fx sine n pi x by L dx. This is the half range Fourier series. Look at over here. This one is the half range Fourier series. So your solution you are getting for the wave equation of one dimension in the form of summation en sine n pi x by L, where an is given by 2 by L, 0 to L fx sine n pi x by L. This is the most important thing, guys. Just look at over here. Again, you guys are least concerned about this method, how we generated this one. No. But once you understood this one, then after you need to memorize only your final solution, wave equation del square y by del t square equal to c square del square y by del x square. And the final solution is this one. And this is the boundary and an, where an is given by 2 by L, 0 to L fx sine n pi x by L. That's it. That's what we want. We just want you to memorize this box. That's it. We don't want all these things. That is just for the understanding. It is not randomly generated. It comes through all this definite process. Any doubt, guys, so far? If you have any doubt, you can ask me, guys.
Sir, I'll be right back. I'm going to use the restroom real quick.
Sure, I can give you 2 minutes, yeah. Is it okay, Jennifer? Jennifer, is it?
Yes, it seems to make sense.
Okay, Mike? Mike, can you hear me?
Yes, sir. I'm picking up what you're laying down.
Garner?
Sir, I'm understanding for the most part what you're saying. I just have to look over the notes again to fully get everything.
Sure. Blaine?
I'm getting it, sir.
Zach, are you okay? Zach? Zach?
Yes, sir. Yes, sir. I forgot I was muted.
Mm-hmm. Did you follow me?
Yes, sir. Yeah.
Okay, good. So that's how this one is generated, because you are in your last semester. So that's why probably you should know how the equation is to be generated. So that's why I proved this equation actually, that how we can get the solution of the wave equation for one dimension. Again, the method is same. Whenever we are going to solve the heat equation, in that case also we will be doing the same technique, and we will be ending up with some type of equations like this. But right now for wave equation for the one dimension, that is given in this form. Okay, guys, shall we start with the example?
That sounds good.
Okay, just look at this example. Read this example 2, 3, 4 times before we start the solution. A string is stretched and fastened to 2 points L apart. In 0 to L is the length. Right? String is stretched and fastened to 2 points L apart. Motion is started by displacing the string in the form y equal to a sine n pi or pi x by L. See, just one n we have considered right now, from which it is released at time t equal to 0. right? Once you pull the string and leave it, so that means just one motion, and then after we have subsequent motions. So that the displacement of any point at a distance x. Now, once you have this string, look at here, guys. Once you have this one, once you put it down like this and then leave it, release it, it will go like this. It will go like this. It will go like this, both sides, right? So that's what it says, that so that the displacement of any point at a distance x from one end at time t is given by this one. Any point x, whatever we have chosen over here, look at here, guys. This is not exactly middle part. No, you can't do that thing. You are slightly out of this middle part, left side or right side of the middle part. So that distance from here, that is x. And this displacement we are looking for, that how much displacement will be there if you do like this. So that is the question. The displacement is given at any point x from one end at time t is given in this form. And then after, if you plug the values of x and t, you are going to get different displacement at different time period, or different displacement at same time, different displacement, different time, like this. So once you have one string, tie the string, one end is 0, second end, the length of the string is L, pull the string, not necessarily in the middle part, just pull the string and release it. That means you will be having some displacement, vertical motion like this, and that is given in the form of this one. At that time, either from 0, from where you are pulling the string, so that is your L, that is your x distance, or here to L, that is x distance. Because once you consider this one here to your pulling part, that is your x, naturally whole length is L, so this distance is L minus x. Or other way around, suppose this distance is x, that means this distance is L minus x. So both the ways you can count it. So that's why I wrote it down here, so that the displacement of any point at a distance x from one end means any other, either this side or other side, at time t is given by this one. Usually we consider 0 as our first end or one end. Okay, shall we start the solution, guys? Look at here. First of all, what are the boundary conditions given to you? You need to first fix the boundary condition, because we are going to use the boundary condition at the initial of the problem. So boundary condition here, first of all, y is a function of x and t. Am I right?
Yes.
Y is a function of x and t. Okay, now x is 0 and x is L. Agree?
Yes.
X is 0 and x is L. So that's my boundary condition. Look at here, when y at 0t and y at LT, that is equal to 0. Because my graph moves like this. So x is equal to 0 and x is equal to L. At both the times, my time t, time function will be 0. Okay, and the initial conditions are, initial condition that is always with respect to, just keep in mind this thing, guys. Whenever you are taking the condition with respect to x, like this, 0 to L, like this, when you change your x, it will provide you the boundary condition. The second variable t is fixed. Other way around, when first variable is fixed and second variable, second t is different, in that case, it will be an initial condition. So initial conditions are yx0. When t equal to 0, it is a sine pi x by L. A sine pi x by L. Because if you take y at t equal to 0 in the given condition, given equation, this cosine t, cosine 0 is 1. So a sine pi x by L. Pi x by L. And if you take derivative, del y by del t will be in terms of this one. So this is constant, sine pi x by L, and here sine is converted to cosine is converted to sine pi c t by L divided by pi c divided by L. Because of this sine and my t equal to 0. So sine 0 is 0, everything is 0. So del y by del t is 0. So I can write like this, my del y by del t equal to 0 when t equal to 0. My del y by del t equal to 0 when t equal to 0. So again, my boundary condition, that is with respect to change in x. So y0t, initial point of the string, final point of the string, t is fixed. That's why it is called the boundary condition, and that is equal to 0. X value is 0. And the initial conditions are yx0, that is equal to a sine pi x by L. y at x0, that is equal to y when t equal to 0, you're going to get this one. And first derivative is equal to 0 when t equal to 0. T equal to 0 gives us this one as well as this one. That's the meaning. When t equal to 0, we have first this one. When t equal to 0, secondly this one. That's why these two are considered as initial conditions. Okay, now as I told you that ready-madely I'm going to use this equation now. You don't have to memorize, go through the whole process. Just try to memorize the last equation. So wave equation solution or solution of wave equation in one dimension that is given by y equal to summation an cosine n pi cd by l sine n pi x by l, where an is given by the half range sine series. Okay. Bless you. So yxt equal to summation an cosine n pi ct by l, right? Cosine n pi ct by l, and sine, look at over here, guys. Here it is n pi x by l. So sine n pi x by l. And an is given by 2 by l. Integration 0 to l y at x0 sine n pi x by l, right? 2 by l fx. Fx is your y at x0. Fx is this one, y at x0. So that's why it is a sine pi x by l. Sine n pi x by l. You know how to solve the half range Fourier series. Just solve this half range Fourier series, find the value of a and go back and plug it over here and you are done. So my half range cosine series, half range, sine series is this one, 2 by l, 0 to l, y x0, sine n pi x by l dx. Okay, yx0 is yx at 0. When t equal to 0, cosine 0 is 1, a sine pi x by l. So plug the value, a sine pi x by l. Sine n pi x by l as it is. This a is constant, just pull it out. So 2a by l outside. Inside the bracket, sine and sine. Sine and sine, that means naturally I can write, see here, 2c minus c equal to negative 2ss. So if I divide and multiply it by negative 2 and negative 2, look at here. Negative 2 and negative 2. Here I have negative 2ss, means I can write this thing in the form of c minus c. Agree? Yes or no, guys? Just Fourier series, our first chapter. So c minus c. So I can write this one, this 2 and 2 will get cancelled out. Negative a by l, 0 to l, and here it is cosine n plus 1 pi x, first addition and then subtraction. So n plus 1 pi x and minus 1 pi x, in between minus sign. In between minus sign. Okay, then we go for the integration. Integration of cosine is sine n plus 1 pi x by n plus 1 and divided by pi by l. So L over pi in numerator. Same here. So L over pi, right? Range of integration is 0 to L. This is 0 to, I forgot to write. It is 0 to L. So if you replace your x by L or like this, at that time, this whole part will get cancelled out and you are going to get, just for n is different from 1, because it is n minus 1, n equal to 1 will not work over here, so n is different from 1. That means you need to count this a1 separately. If you count a1 separately, you're going to get 2a by l, 0 to l, and now a1 separately means n equal to 1. N equal to 1, that means here n equal to 1. So here sine pi x by l and pi x by l. So it is sine into sine is sine square. A is out, 2a by l, sine square pi x by l. So sine square pi x by l. Sine square is written as 1 minus cosine 2 theta. Am I right? Sine square 2 theta is 1 minus cosine 2 theta by 2. Yes or no? Formula sheet, second page, middle part, mostly right side, I think so. Second page, middle part, right side. So 3 formulas are given to you. One is cosine 2 theta is 2 cosine square theta minus 1. Cosine 2 theta is equal to 1 minus 2 cosine square theta. And cosine 2 theta equal to cosine square theta minus sine square theta. Here we are using the second formula. Second formula is sine square theta is nothing but 1 minus cosine 2 theta divided by 2. This is your theta. Pi x by l is theta. So sine square theta is 1 minus cosine 2 theta divided by 2. So that's what I have used over here, because you cannot take the integration of this non-linear function square form. You have to have the linear form. So this is the formula which gives us the linearity of this part. So sine square can be written in terms of 1 minus this one, 1 minus cosine 2 theta by 2. These 2 and 2 will get cancelled out. A by L, sorry guys, A by L is outside, 0 to L, and 1 minus this cosine 2 pi x by L. Just take the integration. Integration with of x with respect to x is simply 1. That is simply integration of 1 is simply x, and here it is cosine 2 pi x by L, that is sine 2 pi x by L divided by 2 pi by L divided by 2 pi by L. So numerator is L over 2 pi, and range is 0 to L. If you plug this value, x is replaced by L. So L here, x is replaced by L, L and N will get cancelled out, sine 2 pi is 0. So simply L over here, otherwise 0. Here it is 0, so 0. So simply L will be there. L and L will get cancelled out, that is simply A. That means my A1 is equal to A. Just go back and plug the value of A1 over there. So yxt equal to A cosine pi ct by L sine pi x by L. That is the solution. It's quite simple. Just whatever you did, you have done in your Fourier series examples, just the same half-range Fourier series. Ultimately, we are solving just half-range Fourier series with some initial and boundary conditions. Additional part is just initial and boundary conditions with half-range Fourier series and plugging the value back over here. That's the only part. Otherwise, it's exactly same whatever you have done in your first chapter of Fourier series. Any doubt, guys? I give you 2 minutes. Just try to look at this one before we start the new example. So many places in your science field or engineering majors, so many places you will be seeing the same type of things in your future. Yeah. There is one more application. As I told you that we started with wave equation in 1 dimension, then heat equation in 1 dimension. Then after we will be switching to heat equation in 2 dimensions, and that will provide us the Laplace equation too. And then after, if time permits, we would like to go over the heat equation in 2 dimensions, and the final application is transmission lines. So those who are over here with electrical engineering major, they will be using these transmission lines, solution of transmission lines in their electrical field using this Fourier series. Probably they will go through this thing in future. I don't know about your undergraduate level courses, but I'm pretty sure that at some point, you are going to use this thing in the future. Maybe in the first year of your graduation course or last year of your undergraduate course. I don't know. I have not gone through all the curriculum of your electrical engineering, but I'm pretty sure it is there. Heating rod, that is the major application of mechanical engineering field. So all you guys engineering, because as I told you that Fourier itself, he was a physicist. And then after, he created a problem based on heating rod, and he found the series whose solution was not available at that time in mathematics. He threw the problem to the mathematicians. Because mathematician couldn't give the proper answer to him or correct answer to him, and that's why he diverted himself to mathematics. He learned complete mathematics and generated the another infinite series, and that is called the Fourier series. So basically, the base started from the application point of view, and that's why you guys are going to use this thing at some point of your life, somewhere. So don't think that these things are not useful to you or like this. Actually, you are learning very advanced things over here. And if you pay a little bit more attention, probably you will find lots of things from this one, lots of things. And if one wants to go through this type of stuff, I think probably you guys will agree with me that he has the knowledge of PDE as well as the Fourier series, because this is the combination of these two. Am I right, guys? Mm-hmm. Right. So that was the ultimate purpose right from the beginning. I've been telling you the same thing, that I have designed this course in such a way, and it is not that easy to derive all these equations. Probably you will not find these type of things in all the books. Sometimes it is hard because every author, different authors, they have used different techniques to prove these equations or solutions. I just proved this one with the easiest method so that you guys can digest this thing at your undergraduate level. But this is the good practice for you guys. And that's the reason I just proved the equation. I spent lots of time just to prove that equation, but I think that's fine. That is worthy. If you can understand this thing, I don't mind to spend some time with you guys. Shall we go for the next one, guys?
Okay.
Ready? Thank you. Second example. Garner, read the example, please. No, but his voice is getting echo, right? Zach, read the example. Garner, are you here? Thank you. Yes, Zach.
A tightly stretched string with a fixed endpoints x equals to 0 and x equal to L is initially at rest in its equilibrium position. If it is set vibrating by giving to each of its points a velocity lambda x equals L minus x, find the displacement of the string at any distance from x from one end at any time t.
Exactly same as the previous example. Am I right, guys? Only thing is you are given the velocity function over here. Del y by del x. Yes or no? That is given to you. That's the only thing. And that's why length is also 0 to L. Length is L. That means my boundary condition remains the same. Y at 0 equal to y at L equal to 0. Agree? Exactly same. And I gave you the, I'm going to give you the example in homework also exactly same way. Once you understand this thing, you won't find any problem solving the exercise examples. Okay. So boundary conditions are this one, yxt, that is, this is my general wave equation solution. You know it, that box, right? Since the string was at rest initially x at 0, x t equal to 0, that is equal to 0. Initially the string at rest, that is given to you. String at rest means when t equal to 0, it is 0, right? So when t equal to 0, initially when x at 0. So if I replace t by 0 here in this equation, t by 0 means this cosine 0 is 1, so an. This is 0 and sine n by x by L. So yx0 will be this one. But yx0 equal to 0, so left hand side is 0. This side is 0 and this is sine an. And cosine 0 is 1, this is 0 and sine n by x by L, sine n by x by L. And this implies that once we have this an equal to 0, an equal to 0. If you plug this an equal to 0 over here, now your series would be of the form yxt equal to summation bn sine n pi ct by L and sine n pi x by L. Bn sine n pi ct by L, sine n pi x by L. Agree? So now ultimately my series is that is of this form because I used my initial condition over here. See, again, I'm telling you that we are using our initial condition, boundary condition in the beginning of the example. In the first example, in the second example, please keep in mind this thing, that we are using this thing at the initial stage of the example before we proceed further. Because once we fix our wave equation or heat equation, what may be, then after we are intending to find just my constant Bn using the Fourier series. That's it. Blaine here. Blaine here. Here, please. Right? Good. Now, as I told you that you are given the velocity function, that means del y by del t is given to you. Am I right? Lambda x and L minus x. Okay, fine. So yxt is this one. Right now, I have this one, equation number 2. Yxt equal to bn sine n pi ct by L, sine n pi x by L. Let me go for del y by del t. So del y by del t, sine is converted to cosine n pi ct by L divided by n pi by L. Oh, so n pi c by L divided by this one. But numerator is n pi c by L. Agree? Divided by this one. And sine n pi x by L. Sine n pi x by L. Okay. So what will happen over here? Let me take this pi c l all outside constant. I'm sorry, my bad. I'm sorry, guys. I made the mistake. I'm not dividing over here. I am taking the derivative, right? I'm not taking integration, derivative. So derivative of sine is cosine n pi ct by L, and my constant is n pi c by L constant multiply over here. Sine of 2t, derivative is cosine 2t times 2. So times 2 is this one, n pi c by L. This is my constant, right? I have this derivative, I'm sorry, not integration. So just multiplication, not division. Good. N pi by L is, oh sorry, nc by L constant, put it out. N is outside, n is inside, pi c by L, constant outside, bn here, cosine n pi ct by L, sine n pi ct by L. So that is my del y by del t. But del y by del t is given to lambda x and L minus x, given to you. Lambda x and L minus x. Initially, the initial velocity is this one. Initial velocity, see, given by giving to each of its points a velocity, this one. It is said vibrating. It is said vibrating by giving each of these, that is equal to this one. Okay. That means, look at here guys, lambda x L minus x when t equal to 0. Plug this value, lambda x L minus x over here. Lambda x L minus x. When my t equal to 0. My t equal to 0, cosine 0 is simply 1. So nbn, and sine n pi x by L here. This is simply 1. Sine n pi x by L. Okay. Pi c by L constant. I can send this one to the other side. So pi c by L and n and bn, right? Or other way around, you can say just simply bn equal to 2 by L, integration 0 to L, lambda x, this is fx, sine n pi x by L. This is my fx. bn, take this one on the other side. So that will be my fx. bn equal to, don't consider this pi c by L times n right now. I already sent all this to the other side. My bn is given by 2 by L, 0 to L, fx. fx is this one. Sine n pi x by L. This is u into v rule. You know u into v rule. This is u, this is v. So derivative of u, integration of v, and alternating sign. Lambda out, x L minus x as it is, u as it is, the integration of v. Integration of v, cosine n pi x by L, and divided by this one, so negative this one. In alternating sign, so minus. L x, derivative of x is 1, minus x square, derivative is 2x, so 2x. Integration of this part, cosine is again sine n pi x by L divided by this square, so square. Derivative of this one is negative 2, alternating sign. Integration is this one. No more integration, 0 to, because now the derivative will be constant. So derivative will be 0 now. So we have to stop over here and 0 to L. 0 to L. If you plug this range 0 to L, you are going to get this 0 to L. You are going to get L minus L is 0. No need to write. Right, guys? Same way, when x is equal to 0, this is 0. So finally, you are getting just this small expression, 1 minus cosine n pi. Cosine n pi is negative 1 to the power n. So you have two parts. If n is even number, because even will give you 1 here, so 1 minus 1 is 0. Right? So 0. An odd number means n equal to 1, 3, 4, 1, 3, 5, 7, 9, 11, blah, blah, blah. That will give you this one. 2 times, so 2 4s are 8, pi, lambda L square n cube pi cube. This one. You can work with this one, or you can write just this n is odd number, you can write 2m minus 1 for all n. M equal to 1, it is 1. M equal to 2, 3. M equal to 3, 5. M equal to 4, 7, like this. So m equal to 1 to, just to take the sequence 1, 2, 3, 4, 5, 6 like this, we can rewrite these odd numbers in terms of like 2m minus 1. So if you write 2m minus 1, my bn will be now this form. Just plug this bn back over here, bn over here, here, and you are done. Yxt equal to this one. So if you plug the value of bn over there, this is your solution. Any doubt in this one, guys? Both examples, they are just parallel, just similar to each other. Only thing is, in the second example, we are given velocity value. velocity value over here. So that's why I took the derivative and I use the value of that derivative. I'm going to say velocity. Any doubt, guys?
Seems to make sense.
Right, guys? If you have any doubt, you can ask me. It's simple. It's just the revision for you guys, because now you know PDE, you know Fourier series. I am just combining both of these things in my applications, and that gives us really good things. See, now what this solution says. This solution says that suppose 0 to L, this is my length. L is equal to suppose 10. L equal to 10 means length of the string is 10 meter, centimeter, what it may be, right? And suppose I take my x equal to 2, right? 10 meter, x equal to 2, and time t equal to suppose 10 seconds, 5 seconds, like this. If I put these values over here, accordingly, I'm going to get the vibration of the string equation over here. When you plug these values over here, different values of this x and t will provide you the position of the string, vibrating string, at some particular time instant. So that will provide you every time. So that is the best way, that is the interpretation of this yxt. Does it make sense, guys?
Yeah, that makes sense.
Good. Just 2 examples, 1 or 2. Well, 2 examples. And again, guys, my first example that is similar to your first example, which I solved. My second example, that is, look at here, I gave you del y by del x equal to fx, right? That is same as here, 2 parts are there. 5 sine pi x and fx 3 sine 2 pi x minus 2 sine 5 pi x. So once you write this, I think you can, if you want to submit just one, I'm good. I don't want you guys to go through both the parts. They are just similar. So pick any one part. I think this will be easier for you. Pick one part and you are done. So both examples, they are just similar. And these are the answers. These are the answers. So your Fourier series, your AN will be of this form, right? Your Fourier series, AN, this is 2 parts are there, and that's why 2 answers are there. Make sense? Right, guys?
Yes.
Now, one-dimensional heat flow. I think we can start heat flow next time, because again, we have simply 7 minutes are left out, and heat flow in 1 dimension, we have to understand this concept, displacement, heat passing from one phase to another phase like this, and how we generate the equation. This is the equation. Only thing I would like to highlight over here, Blaine, only thing is, if you remember here, it was square for wave equation. In heat equation, it's just one order 1. That's the only difference. Please keep in mind this thing. So whenever you see this type of expression, del u by del t equal to c square, del square u by del x square. Del square u by del t square, c square, del square u by del x square. So whenever you see this type of equation, immediately it should be clicked to you that you are talking about some heat equation or wave equation in 1 dimension. Make sense, guys? And all PDE, everything right now, let me talk a little bit about something else. Something else, I mean to say the research area. People are working in PDE since number of decades. Yep, number of decades, last 4 or 5 decades. They have been working for parabolic PDE. Probably you guys don't know, that's fine, but you know the base now. Parabolic PDE, it is something like heat equation. Elliptic PDE, elliptic PDE, elliptic means same order, wave equation type of things. So people are working a lot. People have done lots of control tools and lots of things. PDE is one. Control is one of the tools in MATLAB. So if you enter any PDE with some boundary condition like this, you are going to get the control also. If you install, if you put this equation in the MATLAB, that is easy. Differential equation, that is also one of the tools in MATLAB. So So if you write any differential equation, immediately you get the answer with the figure. Same here. MATLAB, if you start MATLAB, try to write any difference, parabolic PDE, hyperbolic PDE, what it may be, with boundary condition, initial conditions, you will get the figure as well as the answer completely. So there is a tool. Please don't use that tool. If you want to check your answer, that's fine. Otherwise, don't use it. But yes, once you solve this one and then after you can look at that figure and all these stuffs, probably that is the good idea. That's the best idea. So first try to solve this one and then try, just as a curiosity, part of curiosity, try to use MATLAB. Just play on it and enter the equation. Whatever solved, say, look at over here. This is the equation, right? Equation with boundary and initial condition. You will get the graph and everything very nicely. Colorful 2-3 dimensional graph. Okay, so that's the thing. But right now, people are facing lots of problems solving the hyperbolic PDE. Yes, hyperbolic, lots of things are unproved so far in PDE section, in control part also. And that is the problem of the researchers. Researchers have been working in this direction since number of years, number of decades, I would say. They are good so far for all different tools of parabolic PDE and elliptic PDE, but hyperbolic PDE, elliptic also is also a little bit more confusing. Hyperbolic PDE, most of the research papers, people are working in this field. And that's why I told you so many times I've been telling you this thing, that this course is not just for you guys. Of course, we don't offer graduation courses over here at VMI, but this is one of the courses of graduate level. But I think I'm really glad that you guys understood and you guys really worked hard. Credit goes to you guys, yes, that you worked hard to digest this course. That's really good for you guys. I'm glad. But once you understand this thing, the next article, once you are done with your undergraduate, then graduate, and then afterwards the next level, that's the research level. After your graduation, the research starts. Again, research, people working in this field, but at that time you require lots of other things like analysis portion, that is called functional analysis, real analysis, complex analysis. Once you go through all these 3 analysis courses, you will go through in your graduate level course with this type of stuffs. At research level, you are using all this stuff. You are combining all these stuffs to prove your own result. Once you have to generate the result, and then after you have to prove it by your own, and that's called the research. So almost you are on the level of research in future. So I don't say that you will be involved in research tomorrow. No, you need to go through some analysis portion for that. But you are on the right, you are on the track of the research right now. And that's what I told you. You are almost on the base of that line. Right, guys? Anyway, that is just to let you know. I know, don't get scared of these things. It's not that hard. Again, the same thing. We will be using the same tool to get this equation. Then after like this, then after we will be solving this equation like this. Solution of the heat equation. Solution also in this, along the same directions. Look at over here. DPQ and roots are real and distinct and blah, blah, blah. And then after, first example, boundary value, initial value. And second example, boundary value, initial value. And then just the homework assignment. And then just 1-2 examples, not more than 2 guys, just 2 examples. And then after, 2-dimensional heat flow. Most of the heat flow that is in 2 dimensions. I just took it over here first 1 dimension because without 1 dimension, you cannot jump to 2 dimensions. Blaine, please pay attention. Just 1-2 more minutes, right? You cannot jump into the 2 dimensions without knowing the 1 dimension. That's the reason I took in 1 dimension. But if it passes through a road, there is always 2 dimensions, 3 dimensions like this, right? We will discuss this thing next time, guys. But right now, I would suggest you guys to just go through this stuff. Just this one, whatever we did here. Heat equation, wave equation for 1 dimension. Wave equation for 1 dimension. Just read this thing 1 or 2 times. It will give you a lot of ideas. Don't try to attempt the unsolved examples immediately. Try to digest each and every steps of this solution first, both the examples. You will feel confidence. Once you go through the same examples again and again, you will feel more confident. Once you are confident, then after you can try to attempt the unsolved problems. And that will save your time too. You will be confident, one plus point, and you are saving your time. You are solving those examples with the confidence without making mistakes. There's another advantage. So please follow my advice if you want. Yes, guys. So thank you so much. And don't forget to submit your assignment number 1 to 6 before Saturday night, and 7, 8, 9, 10. This is a part of examples, assignment number 7 or 8, something like that. 8, I think so, yeah. So that's due on 30th. So please, please, please try to work with me. Don't keep anything pending. You don't have any other obligation right now except your study. So please pay attention, try to take the advantage of this time because you have full time to study. Take the advantage, and only few days are left out, just 15, 20 days and you're done. So take the advantage of this time, guys. You know, once, see, I always believe in one slogan, and right from my childhood, I kept this thing in my mind. Yeah, it is over here in my mind. If you respect time, time will respect you. If you don't respect time, time never respects you. Never. You have this last 20 days. Just work hard. Put your 100%, all your efforts, and take the advantage of epidemic because you are given you have this opportunity to stay home and try to find your all time with your study. If you are, suppose you were on post at that time, you had lots of other obligations too, right? Right now you don't have any obligations, so just try to pay all your attention on your study, work hard, pay your 100%. Because suppose somebody is getting A grade in all the courses, all the subjects. You know that A grade will appear throughout your life. I mean to say, you can see the certificate throughout your life and you can see, oh, I got A in this course. I got A in all my subjects in my last semester. So that is a credit for you. But suppose you spoil these 20 days and suppose you are getting C in most of the courses. You will sigh throughout your life. And that's why I told you, if you respect time, time will respect you. Trust me, guys, that's my personal observation. I followed this thing. You won't believe, but when I was doing my PhD, you won't believe, I really worked hard. I used to work more than 14 to 16 hours a day. Can you believe it? 14 to 16 hours a day, yes. I skipped my lunch at the time. I didn't have my lunch throughout 5-6 years. Because if I took my lunch for first 2-3 days and I was feeling sleepy. And I was just wasting my 1 or 2 hours. Because I was feeling sleepy, I couldn't pay attention on my work like this. I thought, no, that's not the right way. I stopped taking my lunch. I don't advise you, no, please don't follow me. Please, please, please. I'm just sharing my experience with you. Don't do this thing, but I just want you to take the full advantage of your time. That's what I would like to say. Don't take me other way around, guys, please. Right? If I know something and if I share with you, and if out of your 6 or 7 guys, if 2 guys are taking the advantage, probably I would be glad. I will think that whatever I shared with you, I got something. I know all of you are not going to follow me. I know, but at least 1 or 2, I'll be. Yeah. So please take the advantage. And there is no end of knowledge. Just keep in mind this thing. There is no end of knowledge. If you are in science field, engineering field, mathematics, everywhere, throughout the life, if you read number of books, daily, if you spend 6 hours a day for your own reading throughout your life, there is no end. There is no end. So I don't say that spend all your time throughout your life just for reading. No. Right now you have to take the degree. So that's why just for your undergraduate, graduate level, put your 100%. And then after, when time permits, just try to be in touch with whatever line you have, whatever majors you have. Right, guys? Anyway, I'm sorry I took 3-4 more minutes. I'm sorry. But I will see you on Tuesday, right? And don't forget to submit. Last time I'm telling you, please don't forget to submit your homework by Saturday night, okay? And Jennifer, I will take care of the part.
Yes, I have a still have a question.
Yeah, you can try it if you don't submit. Otherwise, I can create two assignments. We'll do it.
Yeah, that'd be fine. But I still have a question from last time about my homework. So.
Oh yes. What was the question? Tired. I need to work separately for you. What was the question? Will you please give me your question?
Oh, I was just wondering. I always had some issues actually reading the problem for
Reading the problem. Which one? In application or in PDE?
in PDE, the one that I believe it's one where you took pictures of the textbook.
Okay.
And it's number 10.
I can read for you. Just wait. I can read for you. If it is here, let me. Oh, no.
And if it says what I think it's saying, then I'm not exactly sure how to deal with it.
Will you please give me the number? I can read for you. I have that hard copy with me right now. So will you please give me the number?
Number 10.
Number 10. Number 10. Yeah, it is confusing. Let me read for you. Del square y over
Okay.
del x square.
It's an X?
No, it is t. I'm sorry.
Okay.
Yeah, del square y over del t square minus a square del square y over del x square equal to capital E sine pt.
Okay. So how does one convert that into the auxiliary equation? Because it's not dealing with z like we were before, so you can't just use the d operator, can you? Or
Yes, of course you can. Why not?
Huh.
Yes, that's a good question. Everywhere, oh yeah, everywhere you have z. In 10th example, you have y. Oh, okay, that's okay. So del square y, see here, whenever it was, just compare this example with example number 9. It was del square 0 del s square, right?
Mm-hmm. Yes.
Del 0, and del square 0 del s square, that was auxiliary equation. D square minus 2d d dash plus d dash square.
Yes.
Equal to 0. Agree?
Yes, sir.
Instead of z, you have y operator over here. Instead of x, you have t. And instead of t, so instead of y, you have x. So it's a function of y is a function of t and x.
Oh, okay, yeah. So you just...
So we have been taking actually capital D equal to del by del x. Agree?
Yes.
Here we are going to take capital D equal to del by del t. And
okay, so it ends up being just m squared minus a squared?
Exactly.
Okay, and...
So d dash will be del by del x. D is del by del t. And d dash will be del by del x. So I would like to write this auxiliary equation as capital D square minus a square d dash square equal to 0. So I'm good, right?
Yes, sir. And
m square minus a square equal to 0. So m equal to plus or minus a. And let me check example number 10. Yes, I'm right. See, m equal to plus or minus a. So roots are f1 x minus at, f2 x minus at. Look at here.
Because since it should be plus minus, correct? Well, because it looks or at least what it looks like from the scan, it's f1 of x minus at, then plus f2 of x minus at. But since they're identical in this inside the parentheses, shouldn't one of them been?
I think this is a printing mistake. It should be one of them should be x plus at.
Okay, that's good. Okay.
Yeah, it has to be, right? Because our auxiliary equation that is plus or minus at, one has to be plus.
Yes, of course.
Yeah, and second one is e to the power p square sine p. That is damn easy. You can see it very easily. Make sense?
Yes, sir. Okay, that makes much more sense. Thank you so much.
Good, no problem. And Zach, I will again, Zach, just give me some time. And you also work with probably Jennifer or like this, or you can work by your own, and I will solve that example for you. Zach?
All right. Perfect. Thank you.
Yeah, I know that thing, and I will just give me some time. I will solve for you, okay? Any other thing, guys?
Sir, I have a question.
Yes.
So I got stuck on the homework assignment. It was the first. It's homework assignment 1 from the
homework assignment 1.
Yes, sir. It's P tan X plus Q tan Y.
Let me see. Just wait. Homework assignment 1.
I think it's number 3.
Homework assignment 2. I hope. Oh my God, where is 1?
Oh, and speaking of those homework assignments, y'all are doing
yes.
the even. So
yes.
y'all are doing
homework assignment 1. Yes, please. What's the number?
Number 3.
Number 3, P tan X plus Q tan Y equal to tan Z, right?
Yes,
Solve
sir.
the following equation. Yes. Who wants to take this one? Jennifer?
Well, I think actually I think that one was already assigned to us because my,
To you. Okay, then you have answer, right? Just go ahead. How will you
well, I
solve
did,
it?
I think for those first ones, we were all assigned those ones.
Yeah, we all have to do those.
Assignment 1 and 2, we all have the
oh,
same.
never mind. Sorry. Well, either way, I was looking at it and I know, because you end up just having it, you know, tan X, well, basically tan of whatever on beneath everything. So, you know, dx over tan X equals dy over tan Y equals dz over tan Z, right?
Yeah, but it is capital.
And all
Look
it
at
is,
here.
and
Mike, look at here. It is capital P small p plus capital Q small q equal to capital R form. So capital P is tan X, capital Q is tan Y, and capital R is tan Z. So use the Lagrange method, the dx over tan X plus dy over tan Y equal to dz over tan Z, then grouping and integration.
Yeah, and the integration, which I think you might be having the problem with, because you consider that 1 over tan X is just equal to
secant X.
Is equal to cosine of X over sine of X. So it just ends up being the natural, you get to natural log. So
yeah, correct.
That's how you just get over there. So.
Yep. Is it okay, Mike?
I'm still confused on just the form that you used to solve that.
Formula, okay, let me write it down for you. I told you, we are using just the Lagrange method is P plus Q equal to R. So dx by capital P equal to dy by capital Q equal to dz by capital R. This one, look at here.
Okay.
Right? And then after you use the method of grouping, and that's what she said.
Okay, sir. Thank you.
Make sense?
Yes, sir.
Right. Jennifer, would you like to help? Yes. Zach, will you please repeat your question? Assignment number 4. What was the assignment?
It was assignment 2, question 10.
Oh, assignment 2, question 10. Okay. Assignment 2, question 10. Yes, Jennifer.
Is this the one where we're
capital P plus square root of P plus square root of Q equal to 2x.
square? So this is what we're using here. Is this the elimination of a? Are we substituting? Which one is this? Where are we?
This one. Look at here. Number 10.
I don't think I've done that one yet.
You have not done that. You have not done that thing.
I don't think I have, because I've been jumping around a lot when I've been doing my problems. So I haven't actually gotten a chance to write that one out on paper.
Okay.
Or Bree might have taken it because we had to divide them up. Let me check.
Zach, if you use the first method, z square, 8z is there in 8. Here it is capital P and capital Q equal to 2x. So if I take, suppose, first method, z is not there, right? So let me just ignore that z part. Px plus qy and f of pq. Yes, most likely B method will work. Again, I told you, but again I'm telling you, B method will work. Px plus qy equal to square root of 1 plus p plus q square. So if z, that is of the form px plus qy plus f of pq, just replace your p and q by, because it is p and q, sorry, square root of p and square root of q.
You're breaking up a little, sir. Could you repeat that?
I said that B method, you know, A, B, C, D, 4 parts are there. So
yeah, so the z equals px plus qy plus f of pq.
Yeah, px plus q or pq.
Okay.
try to focus on either method A or method B. F of PQ equal to 0 or this one. I think if I use F of PQ equal to 0, then Z equal to AX plus B plus C. So A is replaced by, no, that won't work here, right? A square Y, just X is there. PQXY is this one. P then is fine. Px plus Qy is there. ZPQ, Q and X is there. So Z square equal to PQ, Q square and A square. And if I write PQ, oh, okay. Z.
Sure.
Use method D. F1 XP equal to F2 YQ.
Method D?
Yes, D method. 100% it will work.
Okay, all right.
Why? Look at here. Can I write like this? Capital P minus 2x equal to capital is equal to negative of square root of Q minus 0. Shall I write like this? Just look at the problem.
Must say.
Let me write for you.
Yeah.
See here. Square root of P plus square root of Q equal to 2x. So square root of P minus 2x equal to negative of square root of Q plus 0. Shall I write like this?
Yes.
That means it is F1 PX equal to F2 YQ form.
Okay.
F1 XP equal to F2 YQ form. Or look at here. Yes or no?
Yes.
Right?
Yeah, that makes sense.
Yep. And there's a solution. Now follow this method. Follow this method.
Okay.
Yep.
Sounds good. I'll give it a try.
100% you'll get the answer, because see here you are going to get what? P root P minus 2x. Root P minus 2x equal to some A, right?
Yes.
So that is equal, let me write A. So root P minus 2x equal to A. So naturally, what is my P? My P equal to 2x plus A. Can you find 2x plus A on right side? Yes. 2x plus A. And because of the square root, I'm going to get, I have to make the square. So it is square here. 2x plus A square.
Oh, I see. All right, gotcha.
Right? See,
Yep.
I'm getting, and that's given in the answer too. Look at here.
Yes, and then
Yeah, I got you there.
and then Q becomes A squared.
You're done. You're done. You'll get it. Right?
Yeah.
So just use method D.
Yeah, and if you're still having problems, just ask me about it tomorrow, because I checked and this is actually the last sheet I haven't done out of the problems, because I did in an odd order. So I should have it done by tomorrow.
All right, perfect. Yeah, I'll work on that later tonight and hopefully be finished with it. So
Guys, please work on it. And Jennifer, please make sure, all of you, please make sure about your contribution. How many examples you have solved, your partners have solved. So just please let me know this, please, Jennifer.
Yes.
Sir. All right, thank you, sir.
Right.
Yeah, thank you so much.
I appreciate it. See you later.
See you later. Yeah. Bye, guys. Take care. Stay healthy. Bye.
Bye.
Mm-hmm.